Swayam Prabha. Digital India. Educated India.
This is the continuation of my earlier lecture, so called introductory lecture, where I tried to introduce the subject and the scope of the subject, the materials to be covered, the distinction between traditional as well as advanced ceramics. In my earlier lecture, I started with some topics like a definition of ceramics, then we discussed the generic characterization of the ceramic materials, classification of ceramics. This part we have just completed, but the two more topics which I intend to cover could not be covered. So, in this lecture I will be covering these 2 points, the major raw materials, how we can get the raw materials for both for traditional ceramics as well as advanced ceramics, and then basic principles of manufacturing techniques so far as the ceramics is concerned. We will be discussing these points later on as an individual lecture, but now for the time being we will give you some introductory comments. Raw materials, particularly for the traditional ceramics, are normally naturally occurring raw materials. They are available in nature in different form of minerals. You purify them to some extent and just directly use them for processing of different products. So, what are those products? There are 3 components of natural or traditional ceramics. One is called the plastic materials. It has a property of deformation once you make or once you add some water to this kind of minerals, particularly called clay minerals containing kaolin, talc and so on. When you mix them with some water, it forms a plastic mass. This plastic mass can be deformed without much pressure, even with hand pressure you can deform them and it will not crack. So, the material which is very basically brittle, ceramic material as you have discussed, they are basically brittle, but if you make a kind of mixture of fine powders with some amount of water, it forms a plastic mass and it can be deformed quite easily. However, there are only specific type of raw materials which produces this kind of plasticity, and they are called plastic materials or plastic raw materials. All ceramic materials do not produce or do not give rise to this kind of a property, that also we will discuss. So, it is the clay minerals which is normally give rise to this property and they are called plastic materials. So, they assist in forming process, deform easily without rupture, retain the imposed shape. Examples as I just mentioned is the clay, kaolinite and talc. So, that is one of the major components of traditional ceramics. The second component of the traditional ceramics is called fluxes. They are again raw materials available from nature, some minerals, and their property is or their properties are they melt, they have relatively low melting point, react with other components of the mixture, for example, the plastic mass, the clay, producing a viscous or a glassy liquid. So, when you fire them or heat them at higher temperature, everything does not melt, only the fluxes melt easily and they form a glassy mass. So, this glass also acts as a binder, which acts as a binder on cooling. So, the liquid, the glass is as it is known, it is a viscous liquid, and on cooling it solidifies and binds the rest of the powders. So, flux is the second component of the traditional ceramics products or raw materials for the products, and the example is feldspar. Well, the composition and other things we will discuss maybe at a later stage, but this material is basically contains some alkali metals like sodium oxide or potassium oxide. So, potash feldspar, that is why their names are potash feldspar or soda feldspar, and they act as a flux. The third component is called fillers, which do not melt so easily and at the same time do not produce the plastic mass when it is mixed with water. So, this is actually brittle material, but hard material, and therefore, it produces or develops strength after firing or after sintering. It provides the rigid component to add in forming and firing, because this is the forming, one step is forming. We will discuss the basic principles of fabrication in a few minutes. So, this is the filler material and confers some very important physical properties, for example, thermal expansion, strength and so on, and the example is actually sand. The example is actually sand or aluminum oxide or sometimes lime or even a fired material of this plastic mass, the clays, which are called grog. So, these are actually brittle material, do not have the plasticity, but provides the strength to the body or to the product which you are trying to make. So, these are three different raw materials primarily used for traditional ceramics. One aspect must be noticed or must be remembered that all these raw materials are actually available in nature. We do not have to synthesize specifically or produce these compounds specifically for the purpose. They are available in nature, just we can collect it from the mines and purify it to some extent, little bit of beneficiation is needed, so that the unwanted component of the materials are excluded and purer variety of the particular compound is used as the raw material for traditional ceramics. However, the situation is quite different if we are talking about advanced ceramics. The very basic characteristics of the advanced ceramics or raw material, particularly the raw materials of the advanced ceramics, are they are very pure. They are pure oxides, pure compounds, pure carbides, pure nitrides, pure silicide, borides. So, they are individual compounds and many of them except oxides, many of them do not occur in nature. Therefore, you need special preparation techniques or synthesizing techniques to prepare these oxides, because until and unless you get these materials in pure form and in compositions or the desired compositions or the designed compositions, they do not produce the right kind of property which you are looking for. Therefore, when you are talking about the raw materials for the advanced ceramics group, all of them, most of them I would say, most of them are synthesized. You need different techniques to prepare them. Now, the examples of the compounds, particularly the oxides, when you are talking about electroceramics group, that is one subgroup of advanced ceramics. Here is a list of the compounds which are useful and we exploit different properties to make different devices. The lists are like this. If you are talking about electrical properties, one application area is multilayer capacitors or microwave capacitors. As we have discussed, most of the oxides are insulators, but then every oxide or every compound cannot be used as a multilayer capacitor or a microwave capacitor. They need certain specific properties. This capacitors material which can be used for multilayer capacitors, we will discuss the exact details of the multilayer capacitors, what are the characteristics required for this particular device at a later stage, but for the time being let us see what are the different compounds normally used for multilayer capacitors, because these compounds are known to have a very high dielectric constant. Not only they are insulators, but they have a very high dielectric constant. So, one of the very important compound, once again not available in nature, but can be synthesized by special techniques, is barium titanate. Barium oxide and titanium oxide together forms a compound which is called barium titanate. A similar material is also strontium titanate. Barium is replaced by strontium and therefore, you get another compound strontium titanate. So, these are two mixed oxides, while there is a simple oxide like tantalum oxide also can be used as a capacitor material because of its high dielectric constant. Now, if you are talking about microwave capacitors, they need another very important property, because the energy loss at very high frequencies like microwaves should not be very high. Not only that, that means their dielectric loss must be very low, and higher is the frequency, that is a very critical parameter to be considered. And normal multilayer capacitors like barium titanate, strontium titanate are normally not used in microwave capacitors, but one uses more complex oxides with some different kind of compositions and stoichiometry like barium magnesium tantalate, barium magnesium tantalate another compound with different compositions. I think there is a mistake, it should be titanium, one should be titanium, another should be tantalum. In addition to that, you have barium titanium oxide, another stoichiometry, and it is also another stoichiometry. So, these are some of the materials of specific compositions, specific crystal structures and so on, defect chemistry, all these things are important to give rise to microwave properties. There is another device which is very common in electronics these days, is called FERAM, the random access memory, and FE stands for ferroelectric random access memory. And the material which is used for that purpose is barium strontium titanate, it is a solid solution of barium and strontium titanates. Normally it is prepared or it is used in the form of thin films, not in the bulk material. Then you have ceramic packages. Well, we will discuss what is the purpose of a ceramic package, how it is fabricated and what are the basic requirements of ceramic package, but for the time being it is the insulating property of the ceramics which is utilized for ceramic packages. In fact, ceramic packages are used as an envelope for the silicon microchips. All the silicon microchips have to be covered with some kind of a cover, and it should be isolated from the environment because it is very sensitive. Not only that, but there is a need for electronic connectivity between the microchip and the outside circuit. So, ceramic package provides that particular function. It actually insulates different connections or connecting wires or connecting strips between the semiconductor chips and the outside circuit. And at the same time, alumina is also fairly high conductant, thermal conductant compared to other material. It is also cheap. So, alumina is the material for choice for ceramic packages, extensively used in microelectronics industry. Other properties of ceramics are also important. For example, piezoelectric property. I mentioned earlier that piezoelectricity means you generate voltage, electrical voltage, as you apply mechanical stress. So, those materials are again very useful for many sensors as well as actuators, and these are the compounds: barium zirconium titanium oxide or barium zirconate titanate, or in short PZT, or lead magnesium niobate. These are some of the materials which possesses this piezoelectric property, and they can be used for the sensor and actuators. It is the reverse is also true. As I have just mentioned, piezoelectricity means you generate voltage against mechanical stress. The converse is also true. You apply electric field and you generate mechanical strain. So, the dimension gets changed as you apply the electric field. So, by that process you can make a vibration, you can made to vibrate, you can make the material to vibrate by applying an electric field. So, you can produce noise. Conversely, you can sense the noise. The noise can be sensed by this kind of sensor. Thermistors and varistors, there are another variety of electronic devices, once again utilizes some of the properties of ceramics or ceramic oxides. For example, the semiconducting property of nickel oxide, manganese oxide, cobalt oxide, and barium titanate, doped barium titanate. This is not pure barium titanate. Barium titanate, if it is doped with some amount of other oxides, it can be semiconducting. So, these can be used as what we call thermistors, where the resistance changes quite significantly with temperature. Varistor is another variety of material where the resistance changes with voltage, and that is again has a very important implications or application area, particularly for surge protection. So, the material which is used for this purpose is zinc oxide. Semiconducting property of some of the oxides can also be used for the sensing of the presence of gases, particularly the reducing gases or combustible gases. So, gas sensors can be used by with the use of or exploiting the conductivity, variation of conductivity, electrical conductivity as a function of gas concentration of oxides like tin dioxide, zinc oxide, and then humidity sensor. Humidity sensor can also be measured by, or humidity can be measured by a porous ceramics like magnesium titanate or aluminum oxide, and there you actually measure the variation of capacitance as a function of relative humidity of the environment. You can make oxygen concentration cells or electrochemical cells using some of the solids, some of the solid oxides, like particularly zirconium dioxide. Zirconium dioxide has a very interesting property. It is as a PSZ, partially stabilized zirconia, is a top material, top ceramics, while stabilized zirconia, fully stabilized zirconia with some calcium addition, calcium oxide addition or yttrium oxide addition, it generates or it enhances the oxygen ion conductivity. So, it is no longer an electronic conductor, but an oxygen ion conductor. So, any ionic conductor can be used as an electrolyte, and that electrolyte can be used to fabricate a electrochemical cell. Now, in this case, this oxygen cell, oxygen concentration cell, is used to measure the oxygen concentration of different environments like gaseous environment, or even it can be used in liquid steel. The oxygen content of the liquid steel can be used. So, zirconia is a very important oxide in the area of advanced ceramics. There is another device again using zirconia, it is called solid oxide fuel cell, and that solid oxide fuel cell actually generates power as you burn some fuel electrochemically, not thermally, but electrochemically you burn some fuel, you allow oxygen and fuel to combine electrochemically, and as a result you can generate some EMF. So, that can be used as a source of power, and this is one of the very important application area for non-conventional energy sources, and where hydrogen can be burned and you can generate power without polluting the environment. You do not generate carbon dioxide through the combustion of petroleum gas and so on. So, that is another area of ceramic applications of electroceramics which is coming up. Lanthanum chromite is also a part, in fact it is used as a electrode for this solid oxide fuel cell. In addition to the electrical properties, you have a host of magnetic properties or magnetic materials. They may primarily use for miniature transformer core. In fact, with the use of ceramic magnets, the the size of the transformers have come down by many fold compared to the so called transformer cores made of iron silicon alloys. So, instead of iron silicon alloy, of course, iron silicon alloy is still used in very high power transformers, but miniature transformers for the purpose of different electronics component, I think the only solution is ceramic magnets, either in the radio frequency range or in the microwave range. Okay. So, these are the ferrites, which is called the ferrites, having a spinel structure. We will discuss that structures later on, but these are the compounds. It is a solid solution of nickel ferrite and zinc ferrite, in fact NiO Fe2O3 or zinc ZnO Fe2O3, they form a solid solution of these two ferrites and is used extensively in the microelectronic circuits. Similarly, is the case with manganese zinc ferrite. Well, magnetic tapes and magnetic recording is another very important area of electronics industry, and the material once again the oxides, and we can classify them again advanced ceramics are gamma Fe2O3 and chromium oxide CrO2. These are the materials normally used for recording media and recording heads. Of course, there are other materials these days can be used, it is in the form of fine powder dispersion or in the form of a tape. Okay. So, these are different compounds. I am basically giving you the idea what are the different compounds when you talk about advanced ceramics, particularly the subgroup of electroceramics. We have also another subgroup. I have shown this picture in a slightly different context, but here we are considering the basically the materials, the specific compounds under structural group or where the mechanical properties are important. There are oxides, no doubt, here are some oxides, pure oxides, aluminum oxide, magnesium oxide, zirconium oxide I have just mentioned because of their toughness, and these are insulating materials and fairly strong and cheaper materials, whereas these are mostly available from nature. Aluminum oxide, magnesium oxide, zirconium dioxide, they are all minerals which can be obtained from the natural resources, but they need some purification, they need some beneficiation, they need because the impurity content affects the properties quite significantly. So, the impurities must be removed. Okay. So, once you get from the natural resources, it needs different kind of purification techniques, mostly chemical purification and mineral dressing. Okay. So, mineral dressing followed by chemical purification is the normal technique by which you can get these raw materials from nature. However, there are a host of other structural ceramics compounds or structural ceramic used, the compounds used in structural ceramics. I have mentioned some of them earlier, like boron carbide, silicon carbide, tungsten carbide. Okay. Then you have different forms of silicon carbide and aluminum nitride, okay. Silicon aluminum oxynitride. All these things do not occur in nature. So, you have to prepare them specially to get these compounds. So, the raw materials, the preparation of the raw material itself is a technology there. Okay. So, it just cannot be done only by beneficiation or chemical purification. It needs synthesizing the compounds artificially. So, silicon and carbon has to be allowed to react together, or silicon and nitrogen have to be allowed to react, aluminum and nitrogen have to be allowed to react under certain conditions, and you have then only you can get these pure compounds, and then afterwards they can be fabricated following certain routes and get the different shapes, the desired shapes, either in the bulk form or in the form of some thin films, thick films, or some strips, depending on what is the requirement of the particular application. So, the basic difference between the raw materials of the traditional ceramics and the raw materials for the advanced ceramics, then one can conclude that all the raw materials for the advanced ceramics have to be specially prepared and synthesized following different synthesizing techniques, which I will discuss in a few minutes, whereas the raw materials for the traditional ceramics are available from nature, normally available from nature. With little bit of modification one can go to the product. That is the basic difference so far as the raw materials are concerned. Now, we come to the preparation technique. What is the basic preparation technique used for both for traditional as well as advanced ceramics? Well, if you are talking about pure oxides, primarily for the advanced ceramics group, which I have just discussed, there are different techniques by which one can make high purity oxides. Chemical purification is one route. For example, if you are talking about aluminum oxide, you can just take the bauxite, then remove iron oxide and purify it properly, so that pure form of aluminum oxide can be available to you for even for the advanced ceramic material, advanced ceramic products. There is a technique, we will once again discuss these things later, what are the different consideration, what are the basic synthesis techniques, but there is a technique called sol-gel synthesis, solution followed by gelation. So, it is a solution chemistry route. You take the elements in the solution form, and it may be an aqueous solution, but many a times, most of the times it is a non-aqueous solution in alcoholic medium, and then slowly hydrolyze them, so that the material or the hydrated material or gel forms in a very fine form, in a nanostructure form, and slowly one can heat it to high temperature, so that you can get very fine, almost nano size powders. One has to remember, for any ceramic product, powders is the starting material. So, you need different sizes of powder, different morphology of the powders. Some powders may be very spherical in size, some are angular in shapes, some may be cuboids or hexagonal structures. So, different materials are available in different polymorphic, different geometric form, but their sizes have to be controlled. Preferred thing is one needs a very fine powder, as fine powder as possible. Finer the particle or starting material, it becomes easier for the fabrication, or particularly it can be sintered or fired at a relatively low temperature. So, lower temperature means you save energy. So, that therefore, starting materials need to be fine, and most of the time the particles will be finer than 1 micron size, and these days we are talking about nano size particles as well. So, sol gel is one technique by which you can make either micron size or nano size particles of different oxides or mixed oxides. We will come to that also. Hydrothermal synthesis is another area. It is not just sol gel, but you take a solution and then heat as well as pressurize. So, it is a combination of heating and pressurization. By that process also you can crystallize very fine oxides within the liquid environment, okay, or some kind of a liquid process. Okay. Then there is two processes called spray pyrolysis and CVD. CVD is a short form of chemical vapor deposition. Normally CVD is also another technique by which one can make fine powders. Spray pyrolysis, you just take some, again a solution and spray it, sprinkle it inside a hot chamber or in a flame, so that the particles, the droplets immediately gets decomposed in the hot environment and produces the powders, produces the solid particles which are very fine. CVD is also the same thing, more or less the same thing, but slight difference. It is a chemical vapor deposition inside a chamber, and you decompose it. The chemical is supplied in the form of a vapor, and that vapor at a high temperature is decomposed and you get oxides. So, that oxides can be deposited in the form of very thin films or thick films and so on. So, you can deposit it on a substrate, or you can have freely standing particles. So, these are you use for pure oxides. You have number of mixed oxides, as I mentioned few minutes back. We need different kind of mixed oxides like barium titanate, spinels or ferrites, okay, nickel oxide, iron oxide, barium oxide, titanium oxide, strontium oxide, titanium oxide, and so on. So, they have also to be synthesized following special techniques. One very simple technique is what we call a solid state sintering or solid state synthesis. If you want to make, for example, a barium titanate, you just take barium oxide in the form of carbonate, barium carbonate, and then mix it with titanium dioxide and heat it to high temperature. So, at a high temperature there is a reaction, high temperature chemical reaction between barium oxide and titanium dioxide, and you get a second compound in the form of a mixed oxide called barium titanate. Similarly, if you want to make a ferrite, a magnetic material, magnetic ceramics, you take Fe2O3, pure form of Fe2O3, and then other oxides like zinc oxide, manganese oxide, nickel oxide and so on, and heat it to an appropriate temperature, normally above 1000 degrees centigrade, and maybe in a controlled atmosphere to some extent, so that the stoichiometry can be maintained properly, and you get at the end of the firing you get a compound, mixed oxide compound. Okay. So, this is one of the very simplest way to make mixed oxide, and large number of ceramic oxides have been prepared by this technique. However, one of the difficulty is that you may start with very fine powders, but after the synthesis, after the sintering or after the high temperature reaction, these powders will grow and you end up with relatively large size particles. So, you may not be able to use it properly for its fabrication, and therefore, solid state sintering techniques are not normally preferred these days. Instead, we go for fine powders, so that the sintering, final shaping can be done at a relatively low temperature, and also you get much finer grain size. Okay. We will discuss these things at a later stage, how to the importance of the grain size, what is the importance of the initial particle size or the starting particle size, all these things will be discussed at a later stage, but these are the different techniques by which one can make mixed oxide powders. There are other sol gel which have been used for pure oxides. Once again it can be used for mixed oxides, and the advantage is you get much finer powders. Sometimes one can get very fine but spherical powders, which is very rare occasion actually, and is a special occasion you get to need spherical, you need spherical powders for certain advantages. Now, there is another technique, once again from the chemical route, not the solid state route. It is called co-precipitation, which is very common to the chemists. You precipitate, or you take a mixed ion solution in which both the different ions, metallic ions are present, and then you add some precipitating agent, so that both these ions gets precipitated in the stoichiometric ratio, the ratio whatever we need. So, by that process also co-precipitation has become a very important technique for making some of these synthetic raw materials used in advanced ceramics. Hydrothermal as well as CVD can also be used. Hydrothermal and CVD can also be used for this technique, except that instead of pure oxide you make mixed oxides. However, non-oxide compounds like carbides, nitrides, oxynitrides and so on, they are little difficult to prepare. It is not so easy to prepare them under normal conditions. So, sol gel and co-precipitation, these kind of techniques are not normally used for non-oxide compounds. Instead, we go for carbothermal reaction. Basically, carbothermal reaction is an oxide mixed with carbon and heated to high temperature. It is normally an exothermic reaction, and by that process the metal carbides can be formed. That is a very common technique for making carbides, whether it is silicon carbide, tungsten carbide and so on. They are mostly made by so called carbothermal process, which is nothing but mixing with carbon and then heating it in an environment, a inert atmosphere, so that the carbon does not get oxidized in presence of oxygen. So, oxygen should not be allowed when the reaction is going on. Since if you are talking about nitrides or even carbides, carbon can be taken in the form of solid carbon, or gaseous, maybe carbon monoxide or some hydrocarbons. Hydrocarbons can be taken as a source of carbon and then it can be allowed to react with some metals, so that the carbides can be formed. Solid state reaction of course is always possible, and in many cases solid state reactions, for example, if you are talking about a oxynitride. So, you can take an oxide and then a nitride, silicon oxynitride if you want to make, then you can make from aluminum nitride and silica. So, these two can be or silicon nitride and aluminum oxide. Okay. So, one can make that kind of solid state reactions. Once again, in all these things, because these are non-oxides, oxygen has to be excluded. Oxygen presence of oxygen should not be there, and therefore, that is an important criteria, that whatever you do here, whether it is a solid state reaction, solid gas reaction, carbothermal reaction, decomposition of organometallic compounds, this is another. So, whatever you do, you have to exclude oxygen. The presence of oxygen must be avoided to make non-oxide compounds, which is quite obvious. So, there are many organometallic compounds which can be directly decomposed or pyrolyzed to form some of these non-oxide materials, okay, either carbides, nitrides or silicides, borides and so on. CBD once again can be used for this purpose. So, having discussed the various type of raw material, basically the different compounds required for the preparation of the both traditional ceramics and advanced ceramics. Let us try to see the basic steps necessary for the manufacturing or the processing of ceramic products, or how exactly some products can be made. The important steps are like this. As I mentioned earlier, our starting material is always powders. Okay. It is not lumps, even if the lumps are available, it has to be ground to a very fine powder. So, the starting material is always powder, and since most of the cases ceramics or ceramic materials do have a high melting point. So, melting is always avoided, because it is a very high temperature process and it is not so economic, and therefore, melting is always avoided, but we start with powders. Now, but at the same time these powders must be consolidated enough, so that at the end of the process, end of the fabrication process, you do get a geometrically sound material or mechanically sound material, right. So, this is your first step, the batch. So, you have to prepare some batch, that is you mix some different raw materials. If you want to take mixed oxide, for example, in appropriate proportions must be mixed together. So, you form a batch preparation for the powdery raw material. What you do in case of traditional ceramics, most of the raw materials, as mentioned already, are naturally occurring minerals which need to be beneficiated. For advanced ceramics, normally synthetic raw materials or specially prepared powders of different compositions are used as the raw material. So, these are the raw materials and the basic difference between traditional and advanced. Control of both compositions and the particle size and sometimes particle shape are of tremendous importance. As I mentioned, the chemical composition is important, particle size is important, so that you have the finer particles, so that your starting material have less pores or less open spaces between the particles, so that consolidation and their mechanical strength development becomes easier at a later stage. Then you have different shapes of the particle, sometimes spherical, sometimes more angular, sometimes little cuboids kind of shapes. Many times you can get depending on the crystal structure you can get hexagonal crystals. So, shapes are also important depending on the particular nature of the raw material and the product you want to make. Then the next thing is, once you having get the composition, powder composition, you have to consolidate. That means, you have to give it a shape. The shape is done, the consolidation, the powders normally are mixed with some organic binders. Okay. So, that in the green condition, in the ceramic terminology, green means without fire, which has not been heated. In the room temperature, whatever you do, it is actually green processing, or the shapes which you get and the room temperature, these are actually called green ceramics. And green ceramics, the powder cannot be loose, they have to adhere to each other, and therefore, to facilitate that you get some organic binders. They are mixed followed by application of high pressure using a steel and die punch. So, the depending on the shape and size you need, you have a steel die and punch or a mold in which these powders are compressed under high pressure. The pressures depending on the size and shape and the kind of quality of the product you make, at times you have to prepare thousands of tons of pressure or load to consolidate them. So, this is one of the simplest way to make the powders or the consolidate the powders or give it a shape to the powders. Alternately, powders are suspended in an aqueous or non-aqueous media to prepare a viscous slip. Okay. So, the powders, these fine powders, when you suspend in a liquid medium, normally a kind of electrolyte, water is good electrolyte also for some material, and pour inside a porous mold. Okay. Then this slip, a thick suspension is poured inside a porous mold. Okay. Normally made in case of traditional ceramics, it is the porous mold is made of plaster of Paris. So, you control the porosity, and because of the capillary action, the water which is in which the material is suspended, the particle is suspended, preferentially that water will be absorbed, okay, will be soaked or absorbed inside the pores because of the capillary action, and the powders will get a skin, form a skin on the surface of this mold. So, particularly for prepare a hollowware, if you are talking about a hollowware like a cup or a vase or that kind of thing, if you are making a hollowware, you can always, or even a sanitary ware, okay, that can be made by slip casting using a porous mold. However, very similar technique can also be used for making a very flat sheets. For example, electronics, we have discussed about the packaging techniques or the multilayer capacitors, for which we need a very thin sheet of ceramics, very thin micron size thick, few tens of microns of thick ceramics or thin ceramics I would say. So, these thin ceramics can also be made by starting with a viscous slip, and that viscous slip, of course, in this case most of the time it is not an aqueous slip, it is a non-aqueous slip, a non-aqueous slip made with a volatile liquid or a volatile solvent. So, that slip can be sprayed on a flat surface and you can form a flexible tape. These tapes, because basically it is a composite, it is a composite of some polymeric material in which very fine particles of ceramics are dispersed. So, that tape is flexible to start with, and then you heat it to high temperature when this volatile compound or the polymeric binder will go away, will evaporate out or volatile out, and then you get a stiff, very thin ceramics. So, that is also another technique by which thin sheets can be prepared. Finally, there are several other techniques, as for example, gel casting, cold isostatic pressing, hot pressing, etc., which can also be used under special circumstances. Well, gel casting is also a very similar technique like slip casting, but the compositions are different, but this is again a suspension of fine powders, ceramic powders in some gelatinous gel consistency, okay. A material of gel consistency we have discussed earlier, sol gel technique. So, it is actually a gelation process by which the material gets slowly consolidated and then one can fire it at a higher temperature. Cold isostatic pressing, instead of a what we call a uniaxial pressing, we have earlier says high pressure, here it is basically an uniaxial pressing, and cold isostatic pressing means a pressure from all corners or all sides, and that is can be available with the use of a liquid, okay. A high pressure oil or even mostly oil. You use an oil and inside that you material the powder in the form of inside a bag, flexible bag, you put it there and then pressurize the liquid, so that a uniform pressure is applied from all sides. That has its own advantage, because if the pressure distribution is not uniform and you have a inhomogeneous pore size to start with, at the sintering stage or the firing stage, there will be non-uniform porosity, and that will be a source of weakness so far as the strength is concerned. Okay. So, that is the reason one uses a isostatic pressing. Even this is called cold isostatic pressing, even one can use a hot isostatic pressing. So, you apply isostatic pressure and at the same time simultaneously you heat the temperature, heat the material to a high temperature. So, in this case of course, one cannot use a liquid because it involves high temperature, and therefore, one can have to use a hot gas environment. Okay. So, hot isostatic pressing is one of the latest techniques, and most of the high performance ceramics are made by this hot isostatic pressing. It is quite expensive, but it has its own advantages. Finally, the third stage is basically firing or sintering, that is what is the final or pre-final stage you can say. As the melting point of ceramic materials are relatively high, it should be they are normally not melted and cast to generate a shape. Okay. So, in metals melting and casting is a very common technique for making some shapes, but ceramics being a high temperature material, normally it is not melted and given a shape or cast in a mold. Of course, in some cases we do that, certainly we do that for very special purpose of refractories, or of course glass is another way, but we are not discussing glass here, we are basically discussing the ceramic products. Now, instead of melting and casting, the consolidated powders, sorry there are some mistakes here, are heated to a high temperature for a phenomena called sintering. In this process, the consolidated fine particles form strong interatomic bond with the neighboring particles to form mechanically strong ceramic products. So, this is a common technique, whether you consolidate it by cold isostatic pressing or slip casting or tape casting. Ultimately, all ceramic materials have to be heated to appropriate temperatures, approximately let us say 80% of its melting temperature. Okay. There are different techniques or different mechanisms of sintering. If time permits, we will discuss that later on, but they are specific techniques, sintering techniques or the strengthening techniques of the powders are different for different materials. We will try to look at it at a later stage. So, after sintering, the material becomes mechanically strong and usable, it is actually usable form. Before that, the powders are not normally used. There is the last technique or the last process or step is called finishing, and that is very true, not always, but for particularly for advanced ceramics or structural ceramic materials, because for structural ceramics surface finish is also very important. Surface finish has a very important role so far as the application is concerned, and of course, dimensional tolerance, because you are going through a different processes, the maintenance of dimensional tolerance sometimes becomes difficult, and therefore, there is needs of a surface finishing or finishing of the dimensions primarily to match the requirement of the dimensionality. Under certain circumstances, sintered ceramic articles are required to post sintering finishing operation primarily to adhering to dimensional accuracy and surface finish. So, these are the two things very important for structural ceramic materials, because most of these are engineering components, either a large component or a fine component, and they need conforming to the dimensional tolerance, sometimes very critical dimensional tolerance are very necessary, and therefore, we need finishing operation as well after sintering. So, these are the 4 different steps by which powders, which are prepared by some special techniques as mentioned earlier, can be converted to a product. The product which needs which have the necessary mechanical strength, surface finish, dimensional tolerance, and of course, different kind of designs and configurations. Okay. I think that completes my discussion on the introductory part of this course, which gives you an overall background of what we are going to discuss in much more details at a later stage. In the next class, we will be discussing about the structures. We have discussed some of the compositions of different materials for different purposes, some of the properties and so on. Now, we have to understand how these properties gets developed, why these properties are there, why some ceramics are insulating, others are conducting, others are superconductor. Some have magnetic property and others do not have that kind of property. Okay. Some are very strong, but others are not so strong. So, we need to understand the structure property relationship, and therefore, we start with structure, basic structure of some of these compounds, and slowly develop into how these structures provides you the properties, or we can explain some of the properties we look for. Thank you.